So, in the previous lecture we had discussed the stress tensor. As I said, it has two directions associated with it. The direction of the force itself, stress tensor is defined as the force per unit area. So, sigma I j is defined as force per area in the I direction at a surface with outward unit normal in j direction. Okay. The entire tensor I had written for you in matrix form Ex, Ey, Ez. So, this was the stress tensor, okay, and the force is defined as the force is equal to sigma dotted with the unit normal. So, force at a particular surface with unit normal n is defined as sigma dot n times delta s. Okay. Angular momentum balance, I had shown you that this stress tensor has to be symmetric. Okay, I had shown you from angular momentum balance that this stress tensor has to be symmetric. Okay. And in the absence of flow, okay, for any fluid element you have only a pressure which acts in the compressive direction. The pressure acts along the inward unit normal to the surface, okay, it acts in the compressive direction. Therefore, since it acts only along the inward unit normal, the stress tensor can be written as Ex, Ey, Ez into Ex. Okay. That is for the stress tensor in the absence of flow, the diagonal elements are minus p, the sign negative sign because pressure is defined to be compressive, whereas stress is defined along the outward unit normal. Off diagonal elements are 0. This is what is called an isotropic tensor, that is with equal diagonal elements and 0 off diagonal elements. Okay. And the stress in this case, the force always acts along the unit normal. Okay. In a similar manner, okay, the stress has now got to be related by the constitutive relation to the gradients in the momentum or the gradients in the velocity. Okay. Momentum is density times velocity. So, you can, if the density is a constant, the momentum and the velocity are proportional to each other. Okay. So, the stress has to be related to the gradient in the velocity. Okay. I defined for you the gradient in the velocity is okay, which I had written in matrix form as Ex, Ey, Ez. this whole thing multiplied by Ex, Ey, Ez. Okay, this matrix multiplication will give you the same result as this one. Physically, what does this mean? Okay, so let us go back to our definition of gradients. Okay. Gradient of concentration, for example, okay, in a Cartesian coordinate system. Okay. The gradient of concentration is a vector at a particular location. Okay. It is a vector uniquely defined at each particular location. Okay. So, it is defined as grad C is equal to partial C okay, and it is defined such that if I go a small distance delta x in any direction, okay, delta x vector in any direction, right, C at x plus delta x minus C at x is equal to delta x partial C by partial x plus delta y partial C by partial y plus delta z partial C by partial z. Okay. Just by differentiating by chain rule. Okay. If you go a small distance delta x vector with components delta x, delta y, delta z. Okay. I can also write this quite easily as Ex delta x plus Ey delta y plus Ez delta z dotted with Vx Ex sorry Ex partial C by partial x plus Ey partial C by partial y plus Ez partial C by partial z. Okay. If you take the dot product, you will get delta x partial C by partial x plus delta y and so on, and this is equivalent to delta x dotted with grad C. Okay. So, the change in concentration between two nearby locations separated by a distance delta x, okay, delta C is equal to delta x dotted with grad C. Okay. So, that is the relation. If you go a small distance delta x in some particular direction, there is a change in the concentration. That change in concentration is delta x dotted with grad C. Same thing applies for the velocity vector. Okay. Except now that velocity is a vector, it is not a scalar, unlike the concentration or temperature field. Okay. At some point, okay, I have a velocity v vector. Okay. This is v vector at x. Okay. I go to a nearby point x plus delta x. At this nearby point, the velocity will be different. Okay. So, this is the velocity at x. Okay. At the nearby point, the velocity will be different. This will be v at x plus delta x. Okay. There is a difference in velocity between nearby points, okay, and that difference in velocity, okay, v at x plus delta x minus v at x can be written as delta x dotted with grad v. Okay. Note that both of these velocities are vectors. Okay. Grad v is a second order tensor as I just showed you. Okay. Grad v is a second order tensor as I just showed you. That dotted with a vector delta x gives you the difference in velocity between two nearby points. Okay. You can easily visualize this better by writing it in terms of the components. Okay. So, if I write in terms of Vx at x plus delta x minus Vx at x, okay, is equal to delta x dot grad Vx. Okay. Similarly, Vy, okay, if you consider the components of the velocity as scalars, at x plus delta x minus V y at x is equal to delta x vector dot grad V y, and V z at you multiply the first equation by E x, the second by E y, and the third by E z, and you get this equation, okay, this vector equation for the difference in the velocity between two nearby points. Okay. So, that is the physical meaning of this relationship. Okay. V, the velocity at x plus delta x minus the velocity at x. Okay. Note that when you take the difference in velocities, you have to take the vector difference. Okay. You have to take the resultant vector. For example, in this case, this velocity vector here, I can write it over here. This velocity vector here, I write it over here, and this delta v is the resultant, okay, the vector from this one to this one. Okay. That is the resultant, the vector difference. In the case of concentration and temperature, it was just the scalar difference. In this case, it has to be the vector difference. And why is this difference important? Okay, this difference is important because if the velocity at both locations were equal, okay, if the velocity at both locations were equal, okay, so consider the case where the velocity at these two locations are exactly the same. Okay. That means that this material line element between these 2 points translates to a new position, okay, but there is no stretching or rotation of this material element. Okay. It translates to a new location, but there is no stretching or rotation of this material element as it moves. Okay. It is only if the velocity is different between two locations, okay, that you can see that the material element between these two locations either stretches or rotates or. Okay. Therefore, if the gradient of the velocity is identically 0, okay, that means that the velocity is independent of position. That means that the material fluid elements do not stretch or rotate, and if it is moving as a solid body translation without any stretching, then the stress has to be 0, okay, because for a solid body rotation you cannot generate internal stresses if you move the entire fluid with a constant velocity. It is only when there is stretching of material elements that you will generate internal stresses. Okay. Therefore, the internal stresses have to be proportional to the velocity gradient itself. They cannot be proportional to the absolute value of the velocity, because that is just a constant translation and there is no stretching or bending. Okay. So, therefore, these have to be proportional to the gradient of the velocity. Okay. So, this gradient in the velocity, okay, second order tensor, okay, I told you that this is the second order tensor. Okay. I will consider it as a matrix. I have omitted the unit vectors in front and the unit vectors behind, the row vector in front and the column matrix behind. Okay. This is a second order tensor, just as the stress was a second order tensor. Okay. In the case of the stress, I had told you that it has to be symmetric. In this case, it does not have to be necessarily symmetric. Okay. This does not have to be symmetric. This tensor, any tensor, can be written as the sum of two parts. One is a symmetric tensor plus the other is the antisymmetric tensor. Okay. Any tensor can be expressed as the sum of a symmetric tensor plus an antisymmetric tensor. The symmetric tensor is obtained by taking half of the matrix plus its transpose. Okay. The superscript T is for the transpose of the matrix. Okay. And so, if the transpose is basically when you interchange the off diagonal elements. Okay. Okay, if you interchange these, you get the transpose. Okay. So, therefore, this can be written as half of or okay. The first term will just be partial V x by partial x, because the transpose is equal to the component. This will be half of partial V x by partial y plus partial V y by partial x. Okay, that is the 1-2 term. This will be mistake here. Okay. The third term will be half of partial V x by partial z plus partial V z by partial x. Okay. Then this term will be half of partial V x by partial y plus partial V y by partial x. And then half of okay, so that is the symmetric part. And the antisymmetric part is obtained by taking half of the matrix minus its transpose. Okay. And I should remove the half here, kindly note there is a mistake here, there should be no half. Okay. So, this is basically the 1 1 component 1 2 1 3 okay, of this matrix. Similarly, I can write it for the antisymmetric part. Okay. Note that for the antisymmetric part, the diagonal elements are all 0. Okay. So, this will become diagonal will be 0, half of so there's a mistake here. So, that is the antisymmetric tensor. Okay. So, I will just write the components again for you. Sorry. the diagonal elements are all 0 and the off diagonal elements are opposite in sign to each other. Okay. So, you can see here that these two have opposite signs, these two have opposite signs and these two have opposite signs. Okay. So, that is the decomposition into a symmetric and an antisymmetric tensor. The antisymmetric tensor has 0 diagonals. Okay. Now, the symmetric tensor, okay, can be further decomposed. Okay. The symmetric tensor can be further decomposed. Okay. So, if you recall the symmetric tensor, okay, if I take the sum of the diagonal elements, okay, sum of diagonal elements of symmetric tensor is equal to partial V x by partial x plus partial V y by partial y plus partial V z by partial z. Okay. That is the sum of the diagonal elements of the symmetric tensor, and this is just the divergence of the velocity. Okay. So, this is just the divergence of the velocity. Okay. That is the sum of the symmetric elements. Okay. So, I can write the symmetric tensor as equal to what is called a symmetric traceless tensor. Okay. What is called a symmetric traceless tensor, okay, plus 1/3 divergence of the velocity times the isotropic tensor, okay, where I is the identity tensor. Okay. Recall that I is equal to 1 0 0 0 1 0. Okay. That is the identity tensor, that is the isotropic tensor. Okay. So, therefore, this implies that the extensional strain is equal to the symmetric tensor minus 1/3 del dot V times I. Okay. So, if I take the subtraction, if I take this difference, then E is equal to partial V x by partial x half of this matrix minus of 1/3 del dot V Therefore, I can write this E matrix as partial V x by partial x minus 1/3 del dot V half Okay, so, this is the matrix that you end up with. Okay. And you can see that this matrix, okay, if I take the diagonal, okay, the trace of this matrix is basically the sum of the diagonal elements of this matrix. Okay. So, it is the sum of the diagonal elements of this matrix. The sum of the diagonal elements of this matrix, okay, which is equal to partial V x by partial x minus 1/3 del dot V plus partial V y by partial y minus 1/3 del dot V plus partial V z by partial z minus 1/3 del dot V. Okay. So, I am subtracting out 1/3 del dot V in each case. Okay. So, I get partial V x by partial x plus partial V y by partial y plus partial V z by partial z minus 3 times 1/3 del dot V, which is basically equal to 0. Okay. So, that means that the sum of the diagonal elements of this matrix defined in this manner, the sum of the diagonal elements is equal to 0. Okay. Therefore, this is what is called a symmetric traceless matrix. Okay. So, the velocity gradient tensor can be defined as the antisymmetric matrix, that is the matrix minus its transpose divided by 2, plus a symmetric traceless matrix, okay, plus 1/3 I del dot V. Okay. So, this first is antisymmetric. The second one is symmetric traceless. Okay. And this third one is what is called isotropic. Isotropic because the diagonal elements are equal and the off diagonal elements are 0. So, it is proportional to the identity tensor. Okay. Okay. So, it is proportional to the identity tensor. Okay. Therefore, the gradient of the velocity can be separated out into an antisymmetric, symmetric traceless and isotropic components. Okay. I had told you when we did mass conservation equation that for if the flow is incompressible, the divergence of the velocity is equal to 0 for an incompressible flow. In that case, the isotropic part of the tensor will be 0. Okay. Each of these represents specific types of deformation. In the next lecture, we will continue and see what are the types of deformation represented by each of these. So, I will continue the rate of deformation tensor in the next lecture. I will see you then.